This presentation will be given by Dr. Adam Cegla, also from ETH Zurich, deep learning-based GNSS tomography for high-resolution tropospheric monitoring. Please, Adam.
So welcome everyone. Thank you for this really nice introduction from both Benedict's sides and the presenters. In my today's talk, I will be focused a little bit more on the tropospheric side of our studies related to the tomography algorithm that we are developing. Since some time that is focused on a slightly different way than the presented up to now in the literature, because based on deep learning. And as you may know, the GNSS tomography is rather related with some issues related to the processing, to the fact that we need a proper geometry of the observations, that the computational efficiency is rather low, that we need to add some constraints to the processing, for example, a priori field. And all of those are somehow connected with exactly one issue of tomography processing that is related to the stability of the inversion methods. Because in GNSS tomography, I think you know that, but just as a reminder, we want to solve this basic equation of tomography, which is SWD equal A multiplied by wet refractivity. SWD is the value that we get from the observations, and W is what we want to predict, and A is observation matrix that is strongly connected with the geometry of the observations. If we don't have ray paths of the GNSS signal that are traversing the voxels of the tropospheric model, then the values of observation matrix A are just zero valued, and therefore if we want to calculate NW, want to invert matrix A, we have ill-posed matrix and the problem with the stability of the model. And up to now, a lot of approaches were done in order to solve that problem, connected with adding some new constraints, changing parameterization types to others, or adding some new types of observations. Nevertheless, all of those approaches, however successful to some extent, were adding some more and more constraints to the tomographic model, as well as were based on more and more observations, meaning that the approaches were less feasible. And that's why we decided to completely change this approach, starting from solving the issues connected with this basic tomographic equation, not by solving it like here, for example, shown by least square method or Kalman filters or algebraic reconstruction techniques, but within the framework of deep neural network. And the TomoNet model that I'm going to present you today is the model that bases on the same inputs as the standard tomographic approaches. So we have some a priori wet refractivities, elevation angles, observation matrices, and slant wet delays. Nevertheless, then the neural networks happens, and what is actually happening is processing of two MLPs model, the first one based on the elevation multilayer perceptron, designed to modify the weighting of the observations based on their geometry, and then tomography MLP model that I'm going to tell you a little bit more about in the next slide. The tomography MLP model is designed to predict the increase and decrease branch of the wet refractivity predictions. Decrease meaning that we decrease the a priori field, increase meaning that we increase the a priori field, and then the predicted wet refractivity is shown as an outcome. Tomography MLP itself is based on 6 deep neural network layers. It is activated by ReLU. It is actually a function of matrix A, SWD, elevation, and a priori field, designed to predict these two branches, selected by softmin based on the loss term value. And the loss term value, of course, here is kind of important part of the model itself. The first term is related to the tomography equation itself with the largest value, and terms number 2 and 3 are designed to suppress somehow the unrealistic amplification that may happen of the predicted wet refractivity values based on the a priori field. For those of you who are wondering, these old weights and new weights in the table are related to the fact that the model was the loss term functions were slightly changed before the simulation-based study that was submitted some time ago to the one of the journals. Right now, based on this observation-based study, we decided to suppress a little bit the observation influence itself in favor of the a priori field. Going to the method testing as well as processing. The model was trained using 200 GNSS data station over the area of central part of Poland. Using 5 years of tomographic data, the training set was between 2020 and 2023, and the valid test set was 2024. For let's say validation with some external software, I used Atom tool. Why Atom? Because it's very efficient, and we needed to calculate 5 years of data, so we needed efficient tool in terms of processing time, as well as is the tool that uses simply ground-based approach in least square method. The validation and full depart was made over the area of Poland. However, this is not the same area. The model was moved slightly towards the Wrocław radio sound site in order to validate the results over 2 different years in 2020 and 2021, as well as over the area of California. What is important information is that we didn't change the model, we just used the generalized version of the model over the area of California, so no additional fine-tuning and changing the model was done to obtain the results. And the processing quality can be seen here. Here you can see the time series of ZWD-based validation, meaning that based on tomography output, I calculated the integrated values of ZWD and compared them to the observation. And 2020 and 2021 refers to the area of Poland, while the 2023 refers to the area of California. What is important information that comes from this figure is that Tomonet, so orange lines, works well in all of the cases, all of these scenarios, even in this area of California, as well as over the times and periods where some extreme weather events happened, so these shaded gray areas. Of course, some deterioration of the results happens because here negative values of RMSE means that we are closer to observations. The opposite one means that the results were deteriorated. Nevertheless, those epochs are connected mostly with the areas, with the epochs when lack of GNSS observation was no, or limited number of observations were available to us. On average, the Tomonet presents 20% better results than this least square based approach, as well as up to 30% results or lower RMSE was noted. When comparing to the radio sound observations to the one in Wrocław and Vandenberg in California, such plots can be done and made. Here, once again, orange line refers to the Tomonet, the blue line refers to the Atom tool processing. The Tomonet is especially effective above 2000 meters, where the largest number of intersections between signal happens, which is also a kind of effect that is known from the tomographic-based studies. And based on that validation, we can say that Tomonet produced on average 14% root-mean error lower than the classical approach of Atom. Of course, some of you may also wonder about the spatial capabilities of the model, which is a natural question related to the deep neural networks. And this can be read from that figure, of course, except from a bunch of random dots and statistics shown by this figure. We can also plot cross-section and horizontal cross-section through the tomographic model. And here the true capabilities of the Tomonet are actually presented. Because if you take a look in this particular approach, the horizontal cross-section is done through one epoch at the altitude of 1000 meters. We start from GPT to model as the a priori field. The ERA 5 is given as reference. And the Tomonet output based on weather activities is given in Tomonet panel, while the Atom counterpart in the Atom panel. So as you can see, the Tomonet predicts significantly better those areas of high and low values of weather activities, meaning that the model is also capable of detecting those, which is really important from the point of view of future use of the model itself. And going to the conclusion, Tomonet model successfully outperforms classical tomography approach, at least Atom, in all configurations by increasing stability, reducing root-mean error by an average value of 20% with up to 40% values, as well as I didn't mention it on purpose, but also kind of important thing connected with neural network processing, that the processing time was significantly or even drastically reduced, because up to now with Atom it takes around 4 hours to calculate 1 month of data. of tomography data. In the meantime, for Tomonet, it takes only around 2 seconds. And for those of you who are wondering, why do we need that? Because 4 hours per 1 month is already quite enough and quite fast. If we think about larger or higher density of the tomographic model, here we use 2,700 voxel model, but if you use, for example, 5,000 voxel model, meaning that we double the horizontal resolution of the model, it takes around 4 hours per epoch to calculate it. For Atom, in the meantime, for Tomonet, this is still a few seconds, meaning that with Tomonet, we have a huge prospect for future near real-time processing of the tomography, as well as using significantly higher resolution of the processing. Also, several issues still need to be solved. The best performance is still achieved over the area when the model was trained, so in this particular case, over the area of Poland. Nevertheless, the methodology is quite easy to replicate for the training method, so we can use it once again over the other areas. And for the California, the results were still better than the Atom tool-based solution. As well as neural network model tends to overestimate the true values of reflectivity, especially when the low number of observations is available. But this is also a problem related to the general tomographic approaches as well as the processing. The Tomonet tool is already available on GitLab, so if you are welcome to download it and test it by yourself. And also, if you have any questions related to the model itself as well as to validation methods, you're welcome to talk with me right now when the session is over, or contact me through these credentials on the slide. Thank you.